All right, so we've all played around with tools like ChatGPT, right? But have you ever really stopped and wondered what's actually going on under the hood? I mean, how does a computer just write? Well, today, we're going to pull that curtain all the way back. We're going to build a GPT right from scratch, conceptually, just to see how the magic really truly works. And just to get a feel for what we're aiming for, look at this. This is a real answer from ChatGPT when somebody asked it to write a news article about a leaf falling. It's not just stating facts. It gets the tone, it understands the context, it's even being funny. It's literally creating drama from, well, from nothing. And that really brings us to the central question of all this. Forget just predicting the next word in a sentence. How on earth does a machine learn the subtleties of language well enough to generate something with style, with personality, and yeah, even a little bit of drama? The answer, it turns out, is both way simpler and way more profound than you'd probably think. To get there, though, we have to start at the absolute rock-bottom beginning. We're going to build the simplest language model you can possibly imagine, one that just tries to solve the most basic problem of all, predicting what comes next. So instead of trying to make our model understand the entire internet, we're going to use a much, much smaller set of data, the complete works of Shakespeare. And our goal? It's not to write whole paragraphs. No, it's just to predict the very next character in a sentence. So if the model sees to be or not to be, it should be able to guess that the next letter is E. That's it. That's the whole game. Now, the very first thing you have to understand is that computers, well, they don't read words. They don't see letters. They only see numbers. So step one, always, is something called tokenization. We basically make a dictionary of every single character, A, B, C, a space, a comma, everything, and we give each one its own special number. And just like that, the entire text of Shakespeare gets turned into one giant sequence of numbers. Okay, so we have our sequence of numbers. How do we predict the next one? Well, let's try the absolute simplest, most basic thing we can think of, a big RAM model. All it does is look at one character, the one that just happened, and uses that to guess the next. So if it sees the letter Q, it's going to learn pretty fast that a U's probably coming next. Super simple, right? Yeah, well, it's too simple. And this slide just nails the reason why. To have any chance of guessing the next character after the word me, the model really needs to see the whole sentence that came before it. But our little bigger model, it only sees that final E. It has zero memory, no context. It's like trying to finish a novel when all you've read is the very last word. It's not just a small problem, it's a total dead end. To write anything that makes sense, a model needs context. So how do we give our model that context it so desperately needs? This is where the big breakthrough happens. This is the core idea from that famous paper, Attention is All You Need, that really changed the game. It's a mechanism called self-attention. The idea is this. Instead of just looking at the one token that came right before, what if every token in the sentence could actually communicate with every other token that came before it? What if they could all share information with each other to figure out, as a group, what's important for predicting what's next? Now, this slide breaks down how that talking actually happens, and you can think of it in 4 steps. First, a token sends out a query. It's like a verb asking a question. Hey, I need my subject. Who is it? Second, all the previous tokens offer up a key, like a little name tag that says, hey, I'm a noun over here. Third, when that query and that key match up, it creates a high attention score. And fourth, that high score basically opens up a communication channel, letting the noun pass its value, its information, back to the verb. And here's the really crucial part. This isn't programmed with a bunch of grammar rules. No way. Through a ton of training, the model learns which tokens should pay attention to which other tokens. It figures out on its own that verbs need to look for nouns, or that a pronoun like it needs to find what it is actually referring to. It's basically creating this custom weighted average of all the information from the past, focusing only on what's actually relevant. So where does this incredible self-attention mechanism actually live? Well, it's the beating heart of a component called a transformer block. And this is the fundamental Lego brick that models like GPT are built from. A single one of these self-attention processes is called a head. But why have just one line of communication when you can have a whole bunch? That's what multi-head attention is. The model runs many of these communication channels all at the same time, in parallel. So one head might be figuring out grammar, another might be tracking the main topic of the sentence, and a third might be doing something else entirely. It lets the model gather a much, much richer picture of the context all at once. So a transformer block really has 2 main jobs.
First, it communicates. That's the multi-head self-attention part, where it gathers all that useful context. But then it needs a moment to process all that information. And that's the second step, computation. After all that communicating, each token takes the new information it got and thinks about it, individually, using its own little neural network. This lets it make sense of what it just learned before passing a smarter message up to the next layer. And here's where the real power comes from. You don't just use one of these blocks. You stack them, one on top of the other. The output from the first block, which has a pretty basic understanding of the context, becomes the input for the second block. And that second block builds on it, finding even more complex patterns. You stack dozens of these, and the model develops this incredibly deep, layered, and nuanced understanding of language. Okay, so we now have all the conceptual pieces on the table: tokenization, self-attention, and these stacking transformer blocks. So how do we get from our tiny Shakespeare model to the absolute behemoth that is GPT? Well, the answer really comes down to one word: scale. And the difference in scale is it's staggering. I mean, look at this slide. Our little Shakespeare model has around 10 million parameters, and it was trained on maybe 300,000 tokens. GPT-3, it has 175 billion parameters and was trained on over 300 billion tokens, scraped from a huge portion of the internet. The basic architecture is the same, but the sheer size of the model and the data it learned from is just astronomical. You know, building something like ChatGPT actually happens in two main stages. First is the pre-training stage. That's everything we've been talking about, where the model just learns to predict the next token on that massive data set. That basically creates a really powerful document completer. But then comes fine-tuning. That's where humans come in and give it tons of high-quality examples of conversations, and we rank its answers to teach it how to be a useful and safe AI assistant. Okay, let's zoom out for a second and just put this all together. We've gone from a simple little model that predicts the next letter all the way up to this massive, layered architecture. So when you peel back all of those layers, the magic of GPT isn't really magic at all. It's not some unknowable force. At its very core, it's a surprisingly simple and very clever way for bits of information to figure out how relevant they are to each other. It's really just a weighted average, but it's one that's learned entirely from data and then scaled up to a size so massive that these incredibly complex patterns start to emerge. Self-attention was the key. It gave machines a way to finally, truly understand context. And what we've learned since then is that if you stack these transformer blocks and you just feed them an unbelievable amount of data, astonishing things start to happen. So now that we have this foundational idea, and it seems like we can scale it almost infinitely, the real question isn't how does it work anymore? It's what do we do with it next?